Thank you very much, and welcome everybody. My name is Eric Lanz. I'm an SDK engineer with Embrace. I've been doing software engineering for about 15 years and iOS engineering for 10. I've worked in the gaming, finance, healthcare, telecommunication. I've worked at a ton of different industries. I worked on the WatchKit team at Apple for 3 years, and my greatest accomplishment is I once rode Space Mountain 50 times in a single day. If anyone's curious how you do that, go ahead and ask a question and I'll answer at the end. But I am not here to talk about me today. I am here to talk about memory today. This is one of my favorite topics. I love talking about memory usage because I always hear from junior developers or even some senior developers that since iPhones now have 4 gigabytes of memory, we don't have to worry about this in our applications anymore. We can just write whatever code we want and the iPhone and the operating system will take care of the memory for us. Well, I want to dispel that today. I want to teach everyone here a little bit about the history of how we came to this memory system that we have on iOS, some of the bugs that you can still introduce very easily into your code that can just destroy your performance and even cause your application to crash. Then I'm going to show you how to debug those issues. I'm not just going to leave you hanging there. And then at the end, if we have enough time, I was going to give a quick introduction to virtual memory, which is how memory works on the iPhone and how we're able to run these amazingly powerful applications on such a tiny device. So let's get started. First, what is memory? Well, in hardware terms, memory is a bunch of transistors on a silicon wafer. They're arranged into these little groupings, and then we run electricity through them, and the transistors physically switch from on to off, and we interpret that as a 0 or a 1. But we're software developers, and we don't usually think about the transistors in that way. So we think about memory more as a giant array of zeros and ones that we can jump around in, and we can modify the values of the zeros and the ones. So on this slide, I've represented that as a grid, and I've put an address, which is just an offset in that array. So 1 would be the very beginning of the array, 2 would be the second sort of block in the array. We always separate memory into blocks because it's not efficient to allocate single bits when you're dealing with 4 gigabytes of RAM. So on the iPhone, we actually always allocate 16-byte blocks. And you can try that yourself. If you try to malloc less than 16 bytes, you're going to get a 16-byte buffer because that's the smallest buffer that iOS will give you. For my examples, though, we're actually going to think about memory using 16-bit blocks. So that means each of these squares on my grid has effectively 16 zeros and ones in it. And that means we can store a single 16-bit integer in one of my blocks. Its address would be 1. So if you jump to the address 1 and start reading those bits, you're going to read the value of that integer. If we want to make a 32-bit integer, that's going to take 2 blocks. So address will be 2, and it'll flow through block 3, and whatever we allocate next is going to go in block 4. So for example, here's a 64-bit integer. That's going to take 4 of our blocks. Remember, each of our blocks is 16 bits. And so this has to go at 4. So far, this is pretty straightforward. We're just going to keep filling this grid in. But what happens if we need to delete something? So let's delete that 32-bit integer that we added. Well, we can't move the long at address 4 because other parts of our program are referencing it. So we kind of are left with this gap in memory that we can't really use right now. And in fact, if we go and allocate another long, we have to put it at address 8 because it doesn't fit at address 2. We sort of have this hole in memory that we're just never going to be able to fill unless we allocate a smaller object again. So we call that problem fragmentation. And it's the first problem I want to talk about today because it's one that a lot of developers might have heard of, but probably don't really think about or understand how it impacts their programs. And the way it impacts your program is it makes it slow. And the reason it makes it slow is because those little holes in memory, the more of them that there are, the longer the allocator, which is the program that actually goes and finds a good spot in memory for you, takes to find that spot in memory. So for example, if we write Objective-C code like this, where we're looping 100,000 times, allocating a new string inside the loop, and then logging that string, and then we throw it away, this loop is going to cause intense fragmentation in the operating system as the allocator just keeps running through pages of memory, making new strings and just leaving the leftovers behind. This is really going to slow your program down after this loop finishes, if this loop even finishes, because there's a chance that this loop is going to outrun the allocator because this is a tight loop. It doesn't sleep the thread. It doesn't call out to any other API. It's just looping as fast as it can. And so the allocator is going to try to keep up, but if it can't, the operating system will actually kill this application. And that's, you probably see that as like a watchdog memory kill. You might not be doing exactly this, but this is one way to get that to happen. But you can fix it pretty easily. Objective-C provides the auto release pool block, and that means the opening parentheses and the end parentheses of the auto release pool. When it reaches the end, it gives the allocator a chance to go and clean up memory. So if you add this auto release pool around the inside of the loop's going to be a lot slower because the allocator gets a chance to run instead of your code, but memory is going to be a lot cleaner. What I mean there is the allocator is going to have a chance to go and clean the heap up so that when you go into the next cycle of the loop, it might even use the exact same page of memory for all of these strings, which is much better. But it is slow, so you should think about restructuring the loop even. You could, instead of doing a single loop, have an outer loop go 10,000 times and an inner loop go 1,000 times, and then put the auto release pool in the inner loop so that every 1,000 items you let the allocator run. That might be a better balance of allocator and your code depending on what you're trying to do. So let's summarize that section. Memory is a giant array of addressable blocks. Each block has an address, so you can jump around in there. You don't have to read it linearly. Objects can take up multiple blocks, that's fine. Deleting objects is going to leave space behind in memory. We call that fragmentation and generally think of that as bad. Auto release pool can fix it, but it'll slow you down, so you've got to kind of balance that with performance. So let's move on then to history. So we're going to be talking about the modern allocation system on an iPhone, which is called Arc. But in order to understand how Arc works, we really need to go all the way back to C, which is the foundations of the programming languages we use on the iPhone. When you program in Swift, underneath that, the C allocation runtime is still there managing the objects for you. So we should understand how this works, at least basically. So here's a simple C program. C was all about the keywords malloc and free. Malloc tells the allocator to go and find a spot in memory that will fit whatever you're asking for. So in my program, I'm asking for an integer. So malloc is going to go find a space for an int for me, give me that pointer. I'm going to set it to 42, and then I'm going to free that pointer. So I have direct control over the memory. I tell the allocator when I want something and how much I want, and I tell the allocator when I'm done with it. It's pretty easy to understand. Just to help you understand it even more, I wanted to show you the disassembly of that program. So what I did is I compiled that and then I ran it through a disassembler called Hopper, and we're looking at the C representation of that disassembly. The reason I want to show this to you is because it's almost exactly the same, and that's really the point. If you look at the code I wrote here, it's malloc size of set to 42 free. Here you're doing malloc, you have the free, the 42. It's like exactly the same code. So C lets the programmer manipulate memory in almost exactly the same way as the machine code is going to end up looking. And that gives you a lot of power, but also can cause a lot of problems. So the programmer has to remember to free all of those items. If they forget, it's going to stick around forever. It doesn't matter if it's been 10 minutes since you used something. There's no garbage collection or anything. Nothing's going to come along and clean that up for you. If you don't call free, that pointer is there forever. Pointers are volatile by default. That means anyone can write to them once they've been allocated. It's the programmer's job to protect that pointer using either coding patterns or keywords like const. But this can be very difficult, especially in a multi-threaded environment. You really need to protect access to these pointers when you're working with multiple threads. And I'll show you a bug like that in a few minutes. And then, as we've all heard, it's very easy to introduce a security bug in C, because when you get one of those pointers, you can read before it, or you can try, it will probably crash, but you can also read past the end of the pointer that you allocated. So if you allocate a pointer of size int, you can keep reading past the end of that int and see what's past there. Your program might crash, but attackers may read past it to see if there's a password or something there. We call that a buffer overflow attack. Okay, so C was hard and had a few problems. So Apple came along and invented Objective-C. Objective-C, we call that a superset of C because it sits on top of the C runtime, which I hope you'll see in a few minutes here. But Objective-C looks very different. The keywords aren't malloc and free. Now the keywords are retain and release. And that's because Objective-C uses a reference counting system to manage memory. You might have heard of something like smart pointers. It's very similar to that. where when you allocate an object like this NS number, it has a hidden field associated with it, which is an integer that counts how many other objects are depending on it. We call that a reference count. So that when you first assign the number here, we call retain. That's going to increment the ref count to 1. Then when we call release, that's going to decrement the ref count back to 0. When the count gets to 0, that address is then eligible for reuse by the system, but it's important to know that it is not immediately deleted. So let's look at the machine code for that. Again, it looks very similar. You can see the retain and the release keywords used here. So in a lot of ways, the Objective-C system and the C system are very similar. We're just using different keywords to sort of mark how we're using our memory. There is a key difference though, and that is the ref count is an integer. So in the C world, you could call malloc once, and then you could call free. In the Objective-C world, you can call retain as many times as you want, but you have to remember to call release an equal number of times or the memory will never be let go. And so this is really useful if you're loading objects from a database and maybe you have, your view class, your model class, a table, you maybe have like 5 or 6 different classes using that core data object. Each one of them can call retain on it, and that'll ensure the object won't get released until they're done using it. But the problem is you have to remember all that. So if you have a big team and you have multiple people writing components in your app, they all have to kind of coordinate this retain and release dance to make sure that the release count gets back to 0 eventually, or those objects stay in memory forever. So the multi-threaded work is a little bit easier now because each thread can sort of retain and release the way it wants and make sure the object sticks around. But it still is complex and still has to be coordinated. But now it's the programmer's job. It's a lot harder. The final problem is that when the ref count hits 0, the object's not deleted, it still exists. And it might get reused in a few minutes or a few seconds, but until it does, anything that has a pointer that can try to keep reading it and might crash. And we used to call this zombies because the object is sort of dead, but still there. It's kind of like a zombie object walking around. Yeah, so that can be a difficult thing to deal with. So then we come to where we are today. So today, when programmers start working with Swift or Objective-C, the memory model they're working with is called ARC, and that is automatic reference counting. And now that I've taught you all about what reference counting is, that name should make a lot of sense. It's automatically doing that reference counting work for you. And I'm going to show you exactly how that works. But first, let's look at the same code here, but in an ARC program. So now I can't call retain and release anymore. But I'm still allocating the number, I'm still setting it to 42, and I'm still setting it to nil at the end. So let's see what that generates in the machine code world. So, okay, so the retain call's there. I didn't type retain, but something added retain. So I didn't type it in my program, but there it is in the machine code. And that's the key to how ARC works. ARC is a compiler macro system. It runs at the step after your code has been translated into bitcode, but before your bitcode has been translated into machine code. And in that step, the compiler is going and automatically adding retain and releases for you. But you have to hint it. And I want to show you that here because the keywords we're talking about in ARC are strong and weak. And these are hints that the developer uses to guide the automatic system in managing this memory. Strong is the default. So you notice I didn't type strong or weak anywhere in here, but the machine code used strong. That's because strong is the default. And you have to know that because when you're looking at our code, you won't see these keywords everywhere. But in your head, you have to always be thinking, if I don't see a keyword, it means it's strong. And you can see that right here. Secondly, you can see that the machine code contains 2 store strong calls, both with nil. Why is that happening? Well, let's go back to our code that we wrote again. So we set the object to nil, so that accounts for one of them. But it's actually the closing brace of the main function that accounts for the second one. So ARC works on scope rules, and scope in programs is all about those braces. So when the scope leaves, any object that was in that scope gets automatically released once. So that's why you have to have retained it once in order to keep it around. So that's why we see 2 store strongs of nil in this machine code. So what about ARC system? Are there any problems with that? Well, according to Apple, no. It's a perfect system and it's working great and we don't need to have any problems with it. In reality, though, I think that's probably not quite right, and that's why I'm here today. I want to show you some of the problems with the ARC system. So first, I'm going to show you a bug around unsafe threading. We're going to switch over to Xcode now. So I've got an Xcode project, and I've got a few snippets over here. So this is my unsafe threading snippet. Bring it in. So it's not a very complicated program. What we're doing is we've got an NS mutable dictionary that can store numbers as the keys and values. We're going to dispatch onto the global queue. That just means a background thread. And in the background thread, we're going to read from this dictionary as fast as we can. And then on the main thread, we're going to write to that dictionary as fast as we can. The keys aren't shared between the threads, so this isn't a bug about missing keys or key storage or anything like that. But let me just run this and we'll see what kind of happens. You guys are probably guessing what will happen, and you are right. So first, we're going to see the CPU usage go really high because I am reading and writing very fast on 2 threads. What's happening is the dictionary is growing in size massively. You can see the memory growing here as I add more and more objects to it. But eventually, the program will crash. And that's something that I think we need to understand is this multi-threaded bug is not an immediate crash. It's a random crash that's going to happen if the 2 threads happen to read the same piece of memory at the same time. And so in this case, it took 91 million cycles of this loop in order to hit this bug. So you might think to yourself, oh, this is a really rare bug. I don't need to worry about this kind of bug in my app. But if you have a popular enough app, that you might actually be running this code that many times every day if you have a million users of your application. So you better rethink that. So how can you fix something like this? Well, it's actually really hard to spot this kind of stuff with code analysis or from stack traces, because a stack trace is going to be just an exe bad access, some random place in Apple's code. It won't make any sense to you. But Apple gave us a tool that we can use. So what I'm going to do is I'm going to edit the scheme of this project. So I went up and I'm going to edit scheme. And then I'm going to the run step, diagnostics. I'm going to turn on a tool called Thread Sanitizer. What Thread Sanitizer does is it keeps an eye on those memory reads, and the moment that it detects a memory read happening on 2 threads that is not protected, it's going to stop the program and log that out for us. So what that's going to do is it's going to expose this bug much more quickly so that we can see it without having to wait for 91 million tries or whatever, right? So you see it exposed the bug almost immediately, 6,000 tries. And even better, it tells you, you don't have to guess from the exe bad access stack what's going on. It tells you exactly what you did wrong. So you have a race, that means you're reading and writing 2 different threads. And it's showing here you have read-only access to this dictionary on this thread and here. So this tool will tell you exactly what is wrong. So if you do nothing else, when you leave this talk, please go and turn that tool on in your app if you haven't yet. Run it, run your application, go through some common scenarios. If this thing finds anything in your application, please fix it. It is a real bug and your users are experiencing it no matter how badly you think it's not a real bug. It is real. Okay, so let's move on then to the next kind of bug I want to show you today, and that is retain cycles. So I'm sure you've heard of this. This is the most common kind of problem that you can get with memory and ARC. So let me get my retain cycle code snippet out. I try to make this as simple as possible so we can really focus in on exactly what a retain cycle is and how you cause it and how you fix it. So at first, we're going to show this program working correctly. So what I've got here is I've got a protocol that has just a result ready method. Then I have a class that's implementing that protocol, and it's going to log out the result whenever it gets it. This class then is storing that delegate who implements that protocol and calling out to that delegate on a timer with a 1-second repeat. So every second it's going to call that delegate and tell it the result is ready. So, if we do nothing, what this program should do is every second just print result true, result true, result true, result true, over and over and over again. But I have a check-in here that's just going to print out the delegate became nil when it happens. Because if we go down then to the main portion of our program, I'm allocating those 2 classes and setting the delegate correctly. But then after 2 seconds, I'm going to nil out the delegate. So what I expect to happen is it should print result, true, delegate is nil, delegate is nil, delegate is nil, because the delegate should become nil and it should get released. So let's first run it and see if that happens, and then I'll explain why that happened, and then I'm going to break this program. Okay, works great. So, okay, so why did that work? So that worked because of this weak keyword here. So this is the property that we're storing the delegate on. And remember when I was explaining arg, I was saying that the keywords are strong and weak. Strong is the default, but here we've specified weak. What weak means is that on assignment, we will not increment the ref count. So what's happening here is the delegate class has a ref count of 1. It gets assigned to a weak property which does not increment it, so its ref count is still 1. Then when we set it to nil here, its ref count goes to 0 and gets released. Okay, so let's break this program now. So all I'm going to do is change one keyword. So think about that. One keyword, you might have thousands of files with thousands of lines each in your program. We're just going to change one keyword and break memory entirely in this program. Oops. Apparently, I've broken my program. Okay, well, let's move on to the block capture because I think that'll show this even better. So block capture. Yeah, so block capture is another way to cause this kind of a problem. So here I have almost the exact same setup, but in my main program down here, now I'm sending the class into a second block with a 1-second timer. It's just going to print out the class each time. So let's run this program and see what happens. Yeah, so the delegate is nil. Yeah, okay, so, oh, I'm sorry, it was supposed to have captured that. I think I broke this program last night. Oh, I'm really sorry. Okay, well, let's pretend that it had captured that class correctly, and we can actually make that happen by putting the strong keyword here. Yeah, so now we see that the class is actually is being captured by this block. So because I've added a strong keyword here, when this block was allocated, any variables used inside of the block were captured and will stay in memory, even though it was nilled out here. So what I want to do now is show you how to debug something like this. We're going to use a tool called Memory Graph to do it. And usually you might think of using something like instruments to debug something like this, and that would be a great tool, and I hope to one day do a webinar on instruments. I love that tool, it's awesome, but it's also a little heavy, and I think we can debug this with just the Memory Graph tool that's built into Xcode. So what I'm going to do first is I have to shut off the thread sanitizer because Memory Graph is not compatible with the thread sanitizer. So let's run this again. And we still have the bug. The class is not becoming nil. So I'm going to show you this button here. You might never have pressed this before, these 3 little circles. But if you do, what's going to happen is it's going to capture the heap and it's going to represent the heap over here. Yeah, and so first thing I want to show you before we get into the memory is just how much this program is using. Like, look at all the different modules that are in memory right now. That's pretty crazy. We'll talk about that later, but for now, our module is called memory testers. So let's go and look at that one. We don't have that much in memory. We have the app delegate, we have the scene delegate, we have one view controller. These have complex memory graphs, but the object we're interested in is the class here, which is our delegate. So when you're thinking about a memory bug and you're trying to debug it, you want to answer 2 questions. First, you need to know what is the object that I expected to be released and it wasn't? And in this case, it's a class, it's our delegate. We expected that to be released when we nilled it out, but it wasn't. So we know we have some memory bug around the a class object. So you have to know that first, or memory graph is not going to help you. The next thing you need to figure out is what is holding that object in memory still? Like, what problem did I cause to hold this object in memory? So let's look at that. So that's what memory graph is showing us here. So this is our A class, and this is the thing that's holding it in memory. And we can see it is a malloc block, but we can't see much else. If you look here, it's saying something about malloc stack login is not enabled. So it would be awesome if we could like click on that and get to the code and figure out exactly where the bug is, because maybe the bug was written, you know, while we were out sick or something like that. There is a way to do it. So we're going to turn that on. So we're going to edit the scheme again. I'm going to go back to that diagnostics panel, and we're going to turn on malloc stack. So when you turn this on, it's going to be capturing a stack trace every time we allocate something. And that way, when we run the memory graph, we can look at those stack traces to see where the object was captured. So let's capture another memory graph. And now when we look at this, we have stacks over here. So first here we can see this is the where that class was allocated. And then this is what's holding it. And so now we have a line of code we can go and fix. And immediately it tells us this is the block that strongly captured that object. And in this case, it's because I put a strong keyword here. Excellent. Okay, so that I hope that helps you understand how to look at and debug a memory issue like that. And now, since I think we do have enough time, is that right, Anton? I'm pretty sure we do.
Yeah. Yes, we do.
Awesome. So you guys are in luck, and we are going to talk about virtual memory. This is one of my favorite things to talk about. I think the algorithms around virtual memory, especially on modern devices like iPhones and PCs, are so interesting to think about, and very few programmers ever study them. So I really hope that you find this section interesting. So to start off, let's think of our program as the binary that we created. So in the last example, I was writing a program called memory tester. My binary was called memory tester. It wasn't that big. I only had 50 lines of code. It probably wasn't bigger than 10 megabytes. That should easily fit in memory, right? My binary is going to fit in memory, no problem. But I use Swift when I program, so I need the Swift framework to also be in memory, or I can't call functions on it. So in order for my binary to run, the Swift framework has to be in memory too. Okay, I accept. I also want to use UI views, so I need UIKit. UIKit's kind of big, but I guess, yeah, I guess I need that in memory too. Oh, I want to show a web view on my support page, so I'm going to need WebKit in memory too. WebKit wants to render images, so now I need core graphics in memory. This is getting much bigger than I thought. And now all those images are in memory too. And you can, I hope you can see how even the simplest program is going to load a surprising number of objects into memory. You saw that in that memory graph there. There were 40 plus modules. And in fact, a single view template app from Xcode will load over 3 gigabytes of memory when it loads, before it even starts running. Now, how is that possible? The best iPhone in the world has 4 gigabytes of RAM. How does anything work on that iPhone if programs are using 3 gigabytes of data? Well, the answer is virtual memory. So virtual memory was invented way back in the 1960s to deal with tape drives, because the tape drives were very slow. So virtual memory was a way to sort of have the program be accessing pages that are on the tape while the tape is still spinning to get to those actual pages. And in modern computers, we don't have tape drives anymore, but we still have 2 levels of storage. We have the NAND, which is the hard drive sort of in an iPhone. That hard drive is fast, but it is still orders of magnitude slower than the RAM that's in the iPhone, but it's also much bigger. I have 4 gigabytes of RAM in my iPhone, but I have 128 gigabytes of NAND. So virtual memory lets us use both. And in fact, even more, the virtual memory system on an iOS will let you allocate 1.5 petabytes of memory. Go ahead and try it, you can. You won't be able to write to all of that memory, but it will give you a buffer that big and you can pretend to write to it. So how do these pages work? Well, when you put something in a page, which just means you've called malloc, or in the Arc world, you've initted a new object, that object gets created at an address which is on one of these pages. The pages then are mapped to either real memory or the NAND storage, depending on whether that object is being modified by the program right now. If it's being modified or used by the program, we call that page wired. And what that means is the page is mapped to real addresses in RAM. So it'll be very fast and the program can just use it immediately. But that's not always what we need. Like if we're modifying that image, let's say we're drawing on a gradient on that image with core graphics right now, we don't really need, most of the Swift framework to do that. So the pages that are storing the Swift framework's functions can be mapped out of RAM and back to the NAND storage. And in that case, they're not going to be as fast, but we're not using them right now, so it doesn't really matter. We would rather have that RAM storing the image that we're manipulating. And that's what's so amazing about the virtual memory system, is it is automatically, based on how your program is using these pages, moving them around to optimize the performance of your program and give you this illusion of having nearly infinite memory. Just to finalize that thought and really get it to sink in, I want to explain some of the page types that are on iOS. There's more than this, but these are kind of the main ones. So a wired page is a page that is mapped to real physical addresses. And a mapped page is one that's going to NAND storage. You might have heard of like a mapped file. You might even create mapped files. What you're doing there is just allocating pages of mapped memory to that file. A compressed page is exactly that, is a page that is zipped. You probably didn't even think that was possible, but why should pages of the Swift framework that we haven't called in minutes be fully uncompressed in wired memory? It doesn't make any sense. Why don't we zip those up and store them away? We're not using them anyway. And then finally, a clean page is one that can be recreated from disk. And that lets the virtual memory system do a lot of interesting things with that page. It can compress it, it can evict it to disk, it could get rid of it entirely if it had to, because it knows that at any point it can recreate that page from disk. So those types of pages are ones that go to files or databases or frameworks, because those are static things that might not change. But a dirty page is a page that is controlled by the program. So the second that you touch a page of memory, it becomes dirty. So think about this use case. Think about loading an image from disk and then drawing like a border on that image with core graphics. You've dirtied that page as soon as you draw that border on it. Now that page is dirty. It can't be evicted to disk anymore, even if the virtual memory system thinks that's the optimal thing to do. That's why a lot of times you hear recommendations to use Photoshop to apply your image alterations ahead of time so that you can just load them off disk without having to do manipulations in memory. It's much faster that way. So bottom line is, when you're thinking about memory, think about wired, dirty pages. Those are the only ones that are going to cause your program to be killed by the operating system, because the operating system can get rid of all the other pages without your help, but it can't get rid of the dirty wired pages. And that's why when it sends you a memory warning, you have to release some memory, because at that point, the VM system has done everything it can already, and you need to now help it by getting rid of some of the wired dirty pages. And if you don't, it's going to kill your application. All right, that was a whirlwind tour of memory, and I hope you enjoyed it. I hope you learned something today. I hope you learned how to debug things. And I'm going to stick around now for questions. And